Okay, welcome back to the third and final talk in my surgery theory series. This one's going to be a little more like terse. I'm not going to try to give a lot of details. I think last time I kind of got caught up trying to describe basic homology stuff too much. So this time I'm just going to finish up what I was trying to get to last time and then get to sort of the main goal of this series of talks, and that's to talk about the group of homotopy spheres. Given a dimension, you can think about what are the possible manifolds that are homeomorphic to the standard sphere but not diffeomorphic to the standard sphere. And this group is the set of representatives of those diffeomorphism classes, or more technically, we treat it as h-cobordism classes because it's a little easier to prove things that way, and because of the h-cobordism theorem, in high dimensions, those two are the same thing. So our goal today is to get an actual number for one of these groups and be able to say that this group is cyclic of order this size. That's what we're aiming at today, but also provide tools for you to do the same thing in higher dimensions as well if you wanted to go and try to work that out yourself. So yeah, like I said, I'll start off where we got to last time. I set up a bunch of stuff about manifolds. I introduced their intersection forms. I said it's like a symmetric, non-degenerate, blah-de-blah-de-blah-de-blah bilinear form. So I'll start today by just going over some of the properties of bilinear forms that are essential to the classification of such things. And then I'm going to just cite a theorem that says where our intersection forms fit into the big picture of this abstract algebra.
Can I ask maybe a basic question?
Yes.
So if I have two homotopy spheres, that just means they're homotopy equivalent to a sphere.
Yeah, a closed smooth manifold, which is homotopy equivalent to the sphere.
So if I have like a manifold that's both all these properties manifolds that's homotopy equivalent to a sphere, is it true that it also has to be homomorphism? Like, is it converse true, or do we not?
Let me think. I'm probably going to say some lie. It is true by like higher dimensional Poincaré conjecture. So you prove this using the h-cobordism theorem, actually, that a homotopy sphere is homeomorphic to the standard sphere. Yeah, that's a whole other argument that I just didn't even touch.
Okay, so it is like it properly like classifies them, like not just as in like if they're homeomorphic and they're homotopic to the spheres.
Yeah.
They're in the same class, but also like the other way around also works.
Yeah. So these are. Ask that one again. What did you mean by that?
Okay, because I see how this classifies like the homomorphism classes that are not homomorphic to spheres.
Yeah.
As spheres, but like I'm missing like how coarse is this compared to just looking at like homomorphism classes, mod diffeomorphism classes, as looking at two homotopic like equivalence classes, mod.
Yeah, I should have refreshed myself about that. I think they are the same.
Okay.
Yeah, so a homotopy equivalence of closed smooth manifolds is kind of like a big deal already. So it's really, really close to a homeomorphism, and I think in like the spherical case, you can prove that it is a homeomorphism. Well, at least it's homotopic to a whole, or at least there exists a homeomorphism. Yeah. I think it might be homotopy to a homeomorphism, but I don't know. That's a whole part of surgery theory, studying problems like that. Like if you have a homeomorphism between two smooth manifolds, is it homotopic to a diffeomorphism? If you know that they're already diffeomorphic, can you have like exotic homeomorphisms and stuff like that? For us, in this case, this is like as simple as it can be. Spheres are very, very, very nice. So yeah, this homotopy spheres are the same as just homeomorphic to the standard sphere. Yeah, okay. So aside from that, you can just jump into pure algebra for a moment. Please indulge me. So we're going to talk about bilinear forms because this is the algebraic structure that our intersection form is, that just naturally comes out of thinking about algebraic topology of manifolds via Poincaré duality. So we're going to start with a finitely generated abelian group A. A bilinear form is the usual thing. You just tensor A with itself, take a linear map to Z. That is a bilinear map on A. And I'll use the notation beta squared for just applying beta to an element A in both spots. So since the target of beta is just the integers, any torsion in this group is going to go to 0. So for the rest of this little discussion, we can assume without loss of generality, our abelian group is torsion free. So how do you study these things? There's like a list of properties that a bilinear form could have. Starting off, the one that I keep talking about a lot last time was non-degeneracy. This is the usual thing that you'd see for forms over the reals. You can define a map from your your module to its dual where by check I just mean abelian group homomorphisms to Z. By just taking an A and deciding, okay, I'm going to evaluate on something else by just pairing it with A. And so this map being injective means that this is a non-degenerate form. Or in other words, if you have a B that pairs to 0 with everything else, then that B has to be 0, or A. If A pairs to everything else to 0, then A had to be 0. And this turns out to be equivalent to the condition that the determinant of a matrix representing beta is plus or minus 1. It's going to be an integer matrix, so having determinant plus or minus 1 is a very rare, kind of hard thing to rig up. But it means also that that matrix is an invertible matrix. So non-degenerate can be in all of those things. So you can also ask if your form is definite. So there's either positive definite or negative definite. Just says that anything that's non-zero squares to either plus in the positive case, something positive, or some negative integer in the negative case. And it's indefinite if that is not the case. And this turns out to be equivalent to just saying that there is some element which squares to 0. Some non-zero element that squares to 0. Obviously, 0 goes to 0 because of linearity and all of these things. Last time we were talking about cup product. That's where intersection form came from. The cup product for the intersection form, that form was symmetric, but if you did things in a different dimension, you could get skew symmetric. So symmetry just means it doesn't matter which slot you put them in, you can swap them. Skew symmetric means if you try to swap them, then you get a negative sign. If you think in terms of the matrices representing these, then one is just symmetric and the other is just skew symmetric. It's the same thing. Then we have type. This is something that doesn't exist when you're thinking about forms over the reals, because there's no such thing as even versus odd in the reals. So a form over the integers is going to be even if everything squares, everything even 0. So if everything squares to some even integer. And we're going to say it's odd if you can find a single thing that squares to an odd integer. So it's kind of like as soon as you're odd, if one thing witnesses you being odd, then your type is odd. Otherwise, you're even. Something I could have put at the beginning because it's more basic than all of these things. So this abelian group here, it's finitely generated. The rank of A over Z is finite. And this is what we refer to as the rank of our form B. And now there's one more property, which I didn't define last time. I guess I said I would define it this time. This is called the signature. So if beta is symmetric, then we can diagonalize over the reals. So all of the eigenvalues are real.
Sorry, quick question.
Yeah.
Rank beta equal rank ZA, you mean like it's the map, like this map A to A check? What is rank A? Like the rank as an abelian?
Yeah, like A is just like Z to the rank A.
I'm guessing that doesn't depend on beta. Yes, what is the relation with beta?
You can have like multiple beta on the same thing. Like yeah. So it is really an invariant of the underlying thing. But like if you have two forms that don't have the same rank, then you know like right off the bat they can't possibly be isomorphic because the underlying groups can't be isomorphic. So it's still like a property of your form that you can use to just compare it to other forms and see if they could be the same or not.
So if you have another form like gamma that's also from A times A to Z,
yeah,
it doesn't necessarily have to have the same rank as beta.
It will, yeah. So
because
so two forms on the same module, they're going to have the same rank. Yeah, by definition. Good. Okay. Right. So if beta is symmetric, we can diagonalize it over the reals. So it's going to be isomorphic to something that looks like this. I've chosen to index that lambda 1, and I have to remember to write big, lambda p, and then we start at lambda p plus 1 down to lambda p plus q. Write that better. Where lambda I is bigger than 0 if I is between 1 and p, and less than 0 do I want to say non-degenerate? Let's just say non-degenerate here. Fine. So Sayre's chapter 5 deals with non-degenerate forms. I should have just said that. So we're just going to assume that they're all non-degenerate. So that when you diagonalize it, you don't get any zeros. That's why I want that. So so all of these are going to be positive numbers, and all of these are going to be negative numbers. If p plus 1, p plus q. Okay, and then you define the signature of beta is defined to be the difference p minus q. Okay, kind of a weird thing, but that's what it is. So in this sense, you can see, like, yeah. For example, you might have many different forms on the same module that you can distinguish just by their signatures. So this is a isomorphism invariant. I have to say this so that it's actually meaningful. So if you have an isomorphism to some bilinear form, which I haven't defined, but you can imagine what it means, then the two in signatures have to be the same. Which is in contrast, so this is how it works over R as well. You have signatures for bilinear forms over R. But like I mentioned in my Clifford algebras talk, when you're doing it over the complex numbers, you can always choose a basis so that they're all positive, because you can always just rotate by some unit vector to get into the positive real line. So it's interesting over R. The signature is interesting over R. In particular, it's interesting over Z as well. But to get for the signature over Z, you still have to pass to R, which is fine. Okay, just a little remark about ranks and signatures, I guess. So they're both additive. So you can add together two bilinear forms by just taking the direct sum of their groups, and then you can just sort of take the block sum of their matrices. You can define a pairing from group A paired with group A prime to just be 0 for every A and A prime coming from the two different groups. So if you add them together, I think in my notes I chose to write rank as just R. So I'll continue to do that. So if you take two of them, beta 1, beta 2, well, of course, the rank is just additive because you're just adding the groups together. The signature turns out to also be additive. Because the matrix representation is just going to be a block sum, you can just diagonalize this block and diagonalize this block and count the number of pluses and count the number of minuses. So signature is also additive. This corresponds in manifold land to saying if you have the connected sum of two manifolds, then you add their signatures together. So what else? Here's another remark, is that beta is definite if and only if the signature of beta is equal to, in absolute value, the rank of beta, obviously. Definite means that they're all plus or that they're all minus. So the signature, of course, is in absolute value always bounded by the rank, and it's equal to the rank if and only if it's a definite form. So that's just kind of a nice thing to know. Yeah, maybe I remark about manifolds. So now I can define for a manifold signature. So if M for N is closed, oriented, actually doesn't have to be closed, oriented, and the boundary of M is a homotopy sphere. So homotopy sphere. So something I mentioned last time is when your intersection form, your relative intersection form for a manifold whose boundary is a homotopy sphere is going to be a non-degenerate form. So you can talk about the signature of such a thing, and let's say M and M prime are oriented. Their boundaries are homotopy spheres. Yeah. So you can take their connected sum in the interior. Well, how do I want to say this without introducing new terminology? I'll say boundary connected sum. Sure. I am introducing new terminology. That's okay. So what's the boundary connected sum? Well, it's like the connected sum, except it's on the boundary. So if you have two manifolds with boundary, so if you wanted to do their connected sum, ideally you would choose a point in the interior and then connect them together with tubes, right? Or one tube. But you can do a more clever construction and pick 2 points on the boundary and sort of connect together these two manifolds by a trough. So it looks like this. Here's a little trough. I hope the camera can pick it up this low. Okay, so this is the boundary connected sum. So when you're looking at the intersection form, things that are over here have nothing to do with each other. So if you try to intersect some homology classes that are supported in this half with homology classes supported in this half, they're not like passing over the gap, and then you're just going to get something zero. Yeah.
So I mean, I probably missed this last time, but when the intersection, are you just taking two cycles and like H2MZ or something, and then you just integrate with like, standard integration? Or?
Yeah, pretty much, except it's singular cohomology because you want to use integer coefficients instead of R.
Oh.
So you can't literally use de Rham cohomology, but like all of that stuff is built into singular cohomology already. Yeah. Yeah, so you have your middle dimensional cohomology group, and you pair two things up to the top, and then you evaluate it on the fundamental class that generates the relative group in degree n, which is basically integration. Yeah.
I have a question about your trough.
Yeah.
What I'm doing is I'm taking like an open ball, like in the upper half plane, and just like gluing it together to those open balls.
Yeah, so it's like you're taking two half disks. So maybe if I draw these points a little more over here, you're taking like a half disk there and a half disk there. And then sort of like, yeah. So these two half disks, the boundary of these two half disks are going to be like the two boundary ends of this trough. And so then you can glue in the trough once you remove the half disks. Yeah. And then generalize, let n equal bigger than 2 now, and then, yeah, just do it like that. Yeah. Okay. So in other words, whether they have boundaries or not, right, having a boundary lets you define a relative signature, and if you have a relative signature, it's additive. So if they're closed, in particular, if they're closed and you take the connected sum, then the signatures are additive. And that's just purely because of this. Okay. So now that the stuff's all set up, yes?
Sorry, it's not too easy to me how it falls from that. It's somewhat complicated, the dirks.
This is because, so the intersection form itself is just the block sum of the two intersection forms. That's why, yeah. I don't think I actually explicitly said that, so good question. Yeah.
Maybe I'm missing, maybe the picture is misleading my brain. How is this different from just taking like in this picture, if I would just take like a straight like a planche and just like glue them?
Oh.
I would take a strip or something and just glue them along the boundary.
Yeah, like you just want to take like a boundary and then just bridge it with two strips?
Yeah.
Why is that?
You don't get a mat. It's only a strip.
Like you'd get like corners that you could smooth.
Yeah.
I think doing it this way is more compatible with trying to do it like, so what you could actually do is don't remove the discs, but glue in the trough so that this half kind of glues into this disc, and this half sort of glues onto that half annulus, so that you canonically have a smooth structure that way. But like, I think you're right. I could have just glued on like a rectangle onto the boundary itself. Could I have?
It just wouldn't have been like obvious that you can do you'd have a smooth structure. It wouldn't be as obvious as.
Yeah, it might not be as obvious. Like the boundary that you would get would still be like this outer thing. You'd still get the connected sum. I think it is maybe just like a more sloppy way of doing it. Yeah. I don't know. Picture doesn't look as cool. Yeah, so I wouldn't do it that way. Okay, right. So we set all of this stuff up. So let's see. Let's just recap what we had. Okay, so we had M for n. Boundary of M is a homotopy sphere. So therefore, the intersection form, and oh yes, and we had M is almost parallelizable. All right, like this. It's either a homotopy sphere or it's empty. So if M is not closed, then its boundary is a homotopy sphere. So that's where we are. And we had M is almost parallelizable. So then our list of properties are the following. So we have the intersection form. Yeah. And this went from middle dimensional cohomology, integer coefficients, relative to the boundary. Because the boundary, if the boundary is empty set, then you just get the absolute group. And you take 2 copies of that and you spit out the integers. So this is non-degenerate. It's symmetric. One thing that we mentioned like a couple of talks ago is that it's actually an even intersection form. And so if we want to be able to do surgery, right, the whole point, like you missed the other talks, but the whole idea is if we have a homology class, we want to be able to surgery it away. We can do that if and only if, like, this homology class can be represented by an embedded sphere with a trivial normal bundle. Because that way we can map in the entire tube, like sk cross dn minus k, take out the interior, glue in the complementary thing of like dk plus 1 cross sn minus k minus 1 to do the surgery modification. But in order for that normal bundle to be trivial, we saw that there was a condition that said that this homology class has to have trivial self-intersection. This was the whole reason for looking at the intersection form anyway, is to have this algebraic structure to be able to study these self-intersections of these homology classes. And so if we want to do surgery, we have to have things that have self-intersection 0. So we better have that the intersection form is indefinite. As soon as we have a definite intersection form, we can't do surgery anymore.
What is almost parallelizable?
This means that if you remove one point, then the tangent bundle is trivial. So in particular, if you have any if you have the tangent bundle and you restrict to any like n-1 dimensional skeleton or submanifold, then like that restriction is trivial. Yeah. Yeah. So like if you think in terms of characteristic classes, the only Pontryagin class that can be non-zero is the one in the top degree. So that's going to show up in a little bit. Okay. Oh, I shouldn't have erased that. That's okay. So I'm now going to cite the relevant theorem that handles what happens in this case. It's theorem 5.5 from the book that I just erased. So if beta is all of those things, non-degenerate, indefinite, even, and what is the other one I said? Symmetric. Symmetric. So if the signature of beta is positive, I'm not sure if I actually need this clause or if this is just the way that the theorem stated for simplicity, then there exists a P and a Q so that beta is isomorphic to, oh, I forgot to introduce these. This is going to be good. P times a form called U plus Q times a form called gamma 8, where U is probably the easiest symmetric unimodular even form that is indefinite that you can possibly come up with. And gamma 8, I think for the interests of time, I'm not going to go through the derivation of how you come up with this thing. But it looks like this. I don't know why I want to use the negative one. It's just a convention. You can take the positive one or the negative one. How far down do I go? So you can go run off and check, compute the determinant. It is -1 in this case, I'm pretty sure. And since it's definite, in this case negative definite, the signature of gamma 8, I should have chosen the positive one so I could say that the signature is 8. But in this case, it's -8. So the signature of u here is equal to 0. Because if you diagonalize this over the reals, you get a 1 minus 1, right? But this is the difference between the integers and the reals. You can't diagonalize this over the reals because the 1/2 shows up when you do it. So this does not equivalent to 1 minus 1, which is an odd form. So these two forms are completely different. This is an even form. The one that you diagonalize over the reals is an odd form. Those two are not isomorphic. So this is our classification theorem. And by looking at these two forms, I mean, like I said, this is definite. So if we had a manifold, if beta was a manifold, you'd have all of these things where we have trivial self-intersection and something else that pairs like uniquely with us. So there's a theorem in Kervaire and Milnor, groups of homotopy spheres part 2, that precisely says when one of these things shows up in our intersection form, then we can surger that away. So for a manifold whose intersection form looks like this, we can surger these parts away, and then we can't surger those parts away because that's definite. So this signature is essentially the obstruction to surgering away all of the topology in our manifold. So let me see. What would I like to do? What's the next thing I want to say about that? Yeah. So why don't I just summarize that? Yeah, so Kervaire and Milnor. Yeah, I guess we're leaving Serre now. Now that we have this result, we're leaving Serre and we're going back to manifold land. So I can bring up our primary reference for this. This is Kervaire and Milnor, groups of homotopy spheres 1. And as an exercise for you, go home and write groups of homotopy spheres 2, because it never came out. There's lots and lots of details in this paper that they're like, oh, we'll just do it in part 2. Don't worry, guys.
Is this the famous manuscript one where they like referenced the manuscript for it and then never published it?
It's one of those instances. Yeah. But I think like there was enough floating around out there that experts in the field could piece it together themselves. It wasn't like this big scandalous thing. It's just really annoying for master's students who are trying to learn this for the first time and have no idea what's going on. So in groups of homotopy spheres 1, one of the lemmas is if the intersection form of M is isomorphic to like U plus some other beta prime, then we can do surgery on U. So that if we do the intersection form of the resulting surgery, chi M, is now going to be isomorphic to this remaining thing. So this is what I was just saying about over here. You can get away with the U's until you have this gamma 8 left. So what's interesting about this U and this gamma 8 is that these actually appear as intersection forms of specific manifolds. They're not just some algebraic quirk that's living inside of our manifold. They're actually physically realizable. So if we consider S2K cross S2K, so the cohomology of this manifold with integer coefficients, this is isomorphic to, I like to do it like this, polynomials in AB modulo a squared is 0 equals b squared. So what does that mean? So that means you have a z in degree 0. You have a z plus z in degree 2k. So this one would be generated by your a. This one's generated by your b. And then up in degree 4k, you would have a z that's generated by ab, right? A tensor b. And then you have zeros in between. So the intersection form for such a thing, so S2k cross S2k, okay, well, it's going to be symmetric because our middle dimensional cohomology group is even. This is going to be, right, a squared is 0, b squared is 0, ab is the generator of this, so that's 1, and by symmetry you get 1. So U is actually the intersection form of a product of two spheres. So what this classification is kind of telling you is that however many U's you have in your manifold, that corresponds to, like, you know, taking the direct sum of P many copies of S2K cross S2K. This is giving us our PU part of our intersection form. So now I think Daniel's going to like this part. So how do we make our gamma 8? You're going to like this. How do we make our gamma 8? Yeah, that's good. Yeah. I might mention complex projective space later. So I'm avoiding talking about odd forms just for the sake of time. But if you want to talk about odd forms, they all just look like this. P times just, you know, the identity matrix of dimension n plus Q times the identity matrix of dimension m. And so this is the intersection form of, well, this is the intersection form of complex projective space in degree 2n. And if you take the opposite orientation, you just get the -1. So this intersection form you can just build up by taking connected sums of copies of CP2n and CP2n with the opposite orientation. So that's what happens when you fall into the odd case. So in particular, you can't do surgery on CP2n's because it's not an indefinite thing. So like our story, we don't care about it at all. So I just wanted to do it out of interest. You have a question? CP2?
Yeah, I like CP2.
4 manifold is a really good one. Yeah.
Sorry, can you remind me why between 2k and 4k there's 0?
Because this polynomial ring, right? You have two generators in degree 2k. So nothing can get you into degree 2k and 4 between those two degrees, right? Yeah. It's just because it's a graded ring. Yeah. Okay. Yeah, that was an aside. Don't worry about that. Some flavor text. Okay. So how do we make gamma 8? Answer. This is something called plumbing. So this is a really cool construction. I got to go look up my notes to make sure I don't do it wrong. Maybe. Yeah, probably. So here's kind of the idea. Okay, so let's let n equal 2k. So some even dimension. So we can do 4k plus 2-dimensional manifolds this way. No, I don't. Okay, yeah. Let n be divisible by 4, and let k be half of n. And pick 2 diffeomorphic copies of the k-sphere. Well, I guess I should say 2 k-sphere, right? No, k-sphere, yeah. Okay. So let's pick 2 diffeomorphic copies of the k-sphere. Now pick k-dimensional disk bundles. Say di over si, oriented, or at least orientable disk bundles. and pick local trivializations. Just one for each bundle. Phi I from dk cross dk to di. So you're trivializing this disk bundle over a disk of dimension k, so that let's say phi I circle phi j inverse is orientation preserving.
So are your trivializations going to be opposite for this?
Yeah.
Like, you're taking an open subset of like R2K and mapping it inside DI, or?
Yeah, so what I'm doing is I'm saying, like, I'm picking a disk in the base space, just something that's diffeomorphic to a k-dimensional disk. And I'm saying, okay, let's take the trivial bundle over that, and let's like frame our bundle over that disk using this map. Yeah. So I'll draw a picture. It's going to be a little more clear what's going on with the picture. This is the coolest picture of the world. Okay, so let's take one of the things. Oh, yeah. Yeah, okay. Here's one of my spheres, cross disk. Here's my core sphere. And I'm going to draw my other sphere cross disk like this. Here's my core sphere. And I'm going to choose my trivialization. This is the stuff. Okay. So what I'm going to do is, so here's my disk for this one. So here's my horizontal directions, and here's my fiber directions. Sorry for mixing your chalk colors together, by the way. And now what I'm going to do is, in this manifold, I'm going to interchange the fiber and base directions. I'm going to glue them together like that. So these go with those. Kind of looks like a guitar fretboard. These go with those.
So each of these pink and blue lines are k-dimensional disks?
Yes. Yeah, so these are the fiber disks, and then these are like the horizontal disks. Yeah. So when you glue these together, then you get something like this.
You should really consider a career as an artist.
This is like
I've considered it.
How did you just freehand that all
This is like some like biblically accurate angel.
So there's your plumbed manifold. And I should have emphasized, like, you can, yeah, here's the fact that it's a bundle. It's not just a trivial thing. You can put a twist in it like this.
Yeah, so these like disk bundles, they're not smooth, right?
Sure. Yeah. I could have said smooth, orientable, smooth.
But they don't have to
They
do
don't have to.
In this case, we do because we want to make smooth manifolds.
Oh, sure, okay.
So we want the total spaces to be smooth manifolds so that we can glue them together like this. And then we have some corners here that you can say, okay, we can smooth out those corners.
Could you like sort of glue it on top of some singularities to make it smooth, or
I don't know.
is that like,
I think there's going to be like, I don't know. You have to choose a smooth structure if you want it to be smooth.
Like the orientability assumption can force it to not be like.
Yeah, you can't get that. This is just a schematic diagram anyway because these are not even dimensional. Well, I guess these are, yeah. This is not an option. Yeah, you want it to be orientable. But it's okay. This is just a schematic diagram. So this is the plumbed manifold. So this is plumbing of phi 1, phi 2, say. I didn't come up with a good notation.
Why is it called plumbing?
Because it's like you're putting some pipes together.
Plumbers usually put pipes like that.
I don't think plumbers do anything like this.
Who came up with the terminology plumbing?
I don't know. It could have been like Milnor Kervaire. Kervaire used the plumbing technique to come up with the first non-smoothable manifold. He plumbed together 2 disk bundles over the 5 sphere to get a 10 manifold. Topological 10 manifold with, So what happens? So once you do the plumbing, you have to think about what the boundary is. In this case, because we have it's going to be a circle or 2 circles in this case because there's nothing going on. But you have to think about what the boundary is going to be in terms of the intersection form of this thing that you just came up with. So Kervaire's construction, the intersection form assured him that the boundary was going to be at least a homotopy sphere. But then by trying to glue in a smooth disk, he was able to find some contradiction in terms of the Kervaire invariant, which is something that I don't get to talk about today. So he found some manifold that you can't smooth. Yeah, and then we're going to actually see more examples that are related to that, but they're a little easier to deal with because we can use the signature instead of the Kervaire invariant. Okay, so what are some properties of this? So the middle dimensional cohomology of this plumbed manifold, which I guess I decided to write like this, relative to the boundary, whatever that is. You just have your 2 generators given by your core disks. So pretty much up to homotopy, this thing just retracts onto the wedge of your 2 disks. So if you want, you can even write it like this. So this is Z of the dual of the fundamental class. So you can choose for homology, for instance, you can choose a basis consisting of the one S and the other S. And so you can take the Kronecker basis for the cohomology in this case. So you can just take the duals of these spheres. And so what you get is that the intersection form for Si, comma Si plus 1. So if you take the intersection of the 2 different ones, you get 1. And the intersection squared of Si, well, what is that? You're actually just looking at the self-intersection inside this bundle. Well, what is that? That's just the Euler number of the bundle. So you don't get zeros like we did with the product, but with the product is actually just the plumbing of 2 trivial bundles over the K-sphere.
So when you mean Euler number, you just mean like Euler number of the total space as a smooth manifold, or?
I mean, as a k-dimensional disk bundle, it has a k-dimensional Euler class living in the top cohomology of the sphere. And so you can take that Euler class and evaluate it on the fundamental class, right? So the Euler class of di lives in hk of Si, which is Z. Yeah. Okay, so we have the intersection of such a thing. And then there's some other stuff. Okay, so in general, we can take a graph of spheres with disk bundles. And framings as edges. So these kind of biframings. And plumb them all together. So for example, where do I have that? 1, 2, 3, 4, 5, 6, 7. 1, 2 here. If we put -2s at each of these spots, denoting the disk bundle with Euler class -2, and call plumb. If we plumb this graph and we call that E8, then the intersection form of E8 is our weird form over there, gamma 8.
I was gonna say, I'm guessing because it's gamma 8, that means there's other gammas. There's gamma 1s, there's gamma 2s, there's gamma 3s, or
No. I forget how this works. I think he just chooses the subscript 8 to help you remember that the signature is 8.
okay, it has nothing to do with like this Dinkin diagram E8 or something, or
It has everything to do with E8. So if I actually went through the construction of this, like you actually construct an algebra, which is like, I forget exactly how to say this. It's like the simple root system for the E8 Lie algebra. And so, yeah, the fact that the Dinkin diagram comes up and that like this is the intersection form has everything to do with the E8 algebra.
is there? Sorry,
You're about to ask.
is there like a? I don't know. Maybe you'll get to this, but is there like? Because usually when I see these E8s popping up, at least in my stuff, it's like typically because you have you can form a lattice, like the card group, you get a card lattice, and this lattice, the dual lattice is like some E8 or whatever. Is there like a lattice picture happening in the background?
Probably, yeah. I don't know enough to be able to say yes or no, but probably. Yeah. Okay. Yeah.
What do you mean, like when you say like you plumb this diagram?
Yeah.
Like with itself, then is that?
I mean, yeah. You take 8 copies of the K sphere.
You plumb each vertex together.
Yeah. So the edges, the adjacent copies of the sphere, you plumb them together, and then you just choose like a disjoint framing to plumb with the other one.
Okay.
And then as long as like the dimension is bigger than 1, right? Then your thing is like well defined up to like isotoping these things.
If you asked me for like $1 million to guess what that would have been, E8 would have been like the last thing.
What's the superscript here? 4M. So that's the 4M full product of E8.
4M is coming back here. So that's the total dimension of, yeah. So the K, it's twice, yeah. It's just the dimension of the manifold.
And then what does that mean on E8 then?
I'm saying like you can do this in every dimension divisible by 4.
Okay.
So there's 1 in each dimension divisible by 4. And so dot minus 2 denotes the disk bundle D over S, what do I want? K 2M with Euler class minus 2.
Okay. So the right hand side is just E8.
What do you mean?
Oh, I'm just confused with that notation. So the right hand side is just E8, and then the 4M is just to kind of like denote like what dimension you're at.
Yeah. So it's just, this is the 4M dimensional E8 manifold. Yeah. Okay. So the thing is, okay, so we've realized this really bad intersection form as the intersection form of a manifold. And now what's interesting is that, maybe I want to write this over here so I don't squeeze stuff in. I might want to leave this here. How do I want to handle this? God, Hirzebruch Signature Theorem. Okay, yeah, I should finish off this topic so we can start talking about something else. So I have to remember what I was trying to get at. Does anyone remember what the point was? So the point was I was trying to realize this manifold as the intersection form of something. Yeah, some horrible thing. And we did. So now the interesting thing is, so note, so since this E8 manifold is highly connected, so the first homotopy appears in the middle dimension, and that's the only non-zero homology group until you get to the top relative homology group. And this intersection form is unimodular, so equals I E8 is unimodular. We had We had a fact from last time, sometime. So this is going to imply that the boundary of E8 is a homotopy sphere. I'm going to write homology sphere. Fans of 4 manifolds might be able to tell why. Oh, time to feed the cats. Okay. So E8 in dimension 4, the boundary of this thing is not simply connected. It's a homology sphere, which is not a homotopy sphere. It's called the Poincaré homology sphere. So this thing kind of throws a monkey wrench into a lot of 4-dimensional topology. You have to come up with things called Casson handles in order to like glue a disk onto the boundary of this thing. Yes?
Can you remind me what a homology sphere was?
So this is just a smooth manifold with a map to the standard sphere that induces isomorphisms and homology groups. And it actually is enough to just have a smooth closed manifold whose homology is the same as the sphere. Because you can always choose a little disk, a standard disk in your manifold, and then collapse everything outside of that to get a map to the sphere. And that induces an isomorphism on the only 2 non-zero homology groups. Yeah, so like here's your weird sphere. Here's your standard disk. And then you map to your standard sphere. So here's the hemisphere, maps to this hemisphere. And everything else goes to like this singular point. And so if this is a smooth closed manifold, it's going to turn out that you can actually, the quotient manifold, if you take the fundamental class for this entire manifold and you quotient out everything outside of this disk, then you get the fundamental class for this manifold. So it induces an isomorphism on homology groups. Yeah.
I have a stupid question.
Yeah.
E8 is a Lie algebra, but we're treating like a manifold. So
Oh yeah, this is what I was saying over there. Like, yeah, I'm conflating notation.
Okay, so E8 is what? It's a manifold whose intersection form is
Gamma 8.
gamma 8.
Yeah. So the connection to the E8 algebra for our purposes is kind of incidental. The whole point is we have this really wacky form, and we have a equally wacky manifold with that intersection form.
Because I was gonna say, like, I don't know if this could we just like construct a manifold by plumbing things so that it looks like a Dinkin diagram of like G7 or E2 or whatever, and then we get it corresponding like gamma 2. You know what I mean? Or
Yeah, you could just take any matrix as long as the numbers on the diagonal are like actual Euler numbers of disk bundles. Then you can just take those spheres, and for every entry in the matrix, you just plumb together those 2 corresponding spheres that many times with like orientation preserving or reversing, depending on if it's positive or negative. And you just get any symmetric bilinear, any symmetric matrix you can cook up as the intersection form of some plumbed manifold.
Because if this has significance to E8 just by, this specific configuration of disks, I wonder if other specific configurations have significance to other like Lie algebra. You know what I mean?
Yeah, like you might be interested in checking that out, like find the Dinkin diagrams for the other algebras and just plumb stuff and see what happens. So what's good about this Dinkin diagram, the intersection form that it produces is unimodular. I'm not sure if that's true for the other Lie algebras. Yeah, it's a very, very special thing, E8. So in this case, it is not simply connected, but so for dimension bigger than 4, boundary E8 is a homotopy sphere. So you just have to ensure that the bounding sphere is simply connected, and then it turns out that a simply connected homology sphere is a homotopy sphere. Okay, so that's good. So we can make, so the significance of plumbing to this story is essentially just for making this one manifold that has this minimal signature. So in particular, the signature, in particular, notice that the signature of E8 is, well, it's -8 because I did some stupid stuff and chose the wrong sign convention. So But also notice from Sayre's classification that I just erased, I should have said this immediately so I didn't have to write all these things down again. So if M is, or if beta is non-degenerate, unimodular, I already said that, symmetric, indefinite, even, then because it's like a bunch of copies of U plus a bunch of copies of gamma 8, follows that the signature of beta is actually divisible by 8. Always. And so gamma 8 is sort of the minimal possible one. So this E8 is sort of the minimal possible manifold that you can construct with all of these properties that we're looking for. Okay. Now what? Now what, now what, now what? Okay. So now we're going to start to think about what happens. So question. Is the boundary of E8 standard? Could it be standard? So if it is, we can construct a smooth, closed. Notice that we constructed E8 out of things which were already parallelizable, disk bundles over spheres. And so E8 itself is parallelizable. So we could construct a smooth, closed, and almost parallelizable. M of dimension 4n, which is just, okay, take our E8 manifold of dimension 4n, and then glue in a disk along the standard boundary. And then the signature of M is going to be 8. Okay, question. Is that allowed? Can we make smooth, closed, almost parallelizable manifolds with signature 8? Can we do that? I don't know. Maybe someone can guess based on my tone of voice.
I'm guessing no.
You can't do that. So this is a really interesting and very deep result by Kervaire and Milnor. They figure out the minimum possible signature for such a thing. So they come up with a magic number that I'm going to call Mn, so that any manifold, closed, smooth, almost parallelizable manifold, its signature is going to be divisible by this magic number. And it's going to be a lot bigger than 8. So that's the next topic we jump into now. So this source now, this is right before Kervaire and Milnor's homotopy groups, the groups of homotopy spheres came out. This paper is called Bernoulli numbers. Here they are, finally, Bernoulli numbers appear. Homotopy groups. And a theorem of Rochlin. So there's this classical theorem about spin 4 manifolds and their signatures being divisible by 16. Kervaire and Milnor came up with like a much, much higher octane version of that theorem that holds for higher dimensions. So let's find what my notes were there. Okay. So first recall, okay, so if M 4n is almost parallelizable, so like I said earlier, the Pontryagin class of M is 0 for I less than n, or at least rationally it's 0. So the Hirzebruch Signature Theorem, so recall Hirzebruch Signature Theorem. In particular, we're called the L polynomials. And these were generated by the following power series, where we go. GT is t over hyperbolic tangent of t. We did say this at some point. And if you work out the power series of this is sum over non-negative I, 2 to the 2i, Bernoulli number I, I'm using the topologist's convention for the Bernoulli number. So normally you would see a 2i here, but topologists only care about every other one anyway. So I'm just going to write an I here, divided by 2i factorial, t to the 2i. So the idea is that if you have a line bundle, an oriented two-plane bundle, and you want to know what is the L class of that oriented two-plane bundle, you plug in the Euler class of that. If you have, a bundle, an oriented bundle of dimension 2n, the splitting theorem says you can split that over some splitting space into sum of oriented two-plane bundles. This was in one of my talks, so I get to just say it verbally. And so for each of those two-plane bundles, you apply this formula, and then since the Pontryagin classes are the elementary symmetric polynomials in these formal roots, what you do is then you multiply the power series together, collect together terms, write it in terms of elementary symmetric polynomials, and then you get a polynomial called the L class. So this is a whole story. I spelled this out one time. I don't have enough time to spell it out again, but I will if people have more questions. It's a really nice calculation to just sit down and do it. So the point is that from Hirzebruch Signature Theorem, we get really numerical stuff, and this is where the Bernoulli numbers show up. And so this is a polynomial in the Pontryagin classes, P1 up to Pn, with the property that if you plug in the fundamental class for your manifold, then you get the signature of M. So this is sort of, I'd love to call this classical, but I know that this is not familiar to everybody, but this is one of the really big results from the 60s that Kervaire and Milnor use. So Hirzebruch also established in his book so maybe if I have time later in this month, I can present this calculation. So the coefficient of Pn in which Ln is the following. It almost looks like this coefficient, but for magical reasons, you have an extra 2 to the 2n minus 1 Bernoulli number. So I'm going to call this number Ln for L polynomial. All right? So this is a number. It depends on n. And this is the coefficient of Pn. So therefore, so M almost parallelizable, means that the signature of M is equal to this coefficient, Ln, times the top Pontryagin number of M, and then plus lower degree terms in terms of the lower Pontryagin classes. And so those are all 0 because it's almost parallelizable. So just from Hirzebruch signature theorem, the assumption of almost parallelizability tells us that our signature of our manifold is this fixed magic number times whatever the Pontryagin class of M is. And so what Kervaire-Milnor answered, so Kervaire-Milnor said, what is the minimal PNM? So can we find a divisibility result that says that for any of these manifolds that we want to think about, particularly the ones we want to think about, is there a number that divides all of these? And so now I'm just going to throw some words at you and then calculate some stuff. Okay. So now enters one of the other huge key pieces of differential topology that I haven't gotten to yet, This is called the J homomorphism, aka the Hopf-Whitehead homomorphism. So the real important incarnation of this homomorphism is via the Pontryagin-Thom construction, which, like, I've never even mentioned that before, so I'm going to describe it in a different way and just cite some results. Because, you know, Pontryagin-Thom is another one of these massive, massive important things that I just don't have time to talk about today. Also called the, sorry? Maybe. Yeah, I'm looking forward to releasing the next manuscript of Home Surgery Theory Part 4. Homomorphism. Okay, so here's the easiest way to write down the definition, even though it's not necessarily the most enlightening. So ON, sure, everybody, his own page, this acts on Rn, and this extends to the one-point compactification of Rn, which I'm just going to write as Sn. And it fixes 0 and the point at infinity. Okay, so this action we express by, okay, we take an operator and an element in this one-point compactification, and we send it to an element in the one-point compactification.
Should it be Sn minus 1?
I forgot to write a plus. Yeah, no, yeah, naturally it does. It does naturally, but I'm thinking about the one-point compactification of Rn.
Because you're just adding the point.
Yeah.
Yeah, so just
Yeah, so I want to do this so that it has a fixed point. So if we choose 0 as the base point of this manifold, then notice that ON, so everything in ON fixes the base point, and the identity fixes everything in Sn. And so this wedge product goes to the base point of Sn. Therefore, by the universal property of the quotient, you know, by definition, this quotient is the smash product. This action actually descends to the smash product. Why is that good? Well, now if we pick a map from Sk, some arbitrary k, to On, we can form the following. J alpha goes from Sn plus k, do I want k plus n? Whatever. So this is homeomorphic to the smash product of these two spheres. And then we can take our alpha into On. Actually, I did want the other way around. I do want the other way around. Okay? And we can take our alpha and just smash with the identity function to get into On smash Sn. And now we take our action. Now we just act to get back to Sn. So we started with an element in pi k of On, and we ended up with an element of pi n plus k of Sn. Kind of weird, right? So I'm going to draw a diagram to sort of, well, I'm not going to illustrate how this action works. You know how the action works. I'm just trying to get words on the board so that I'm not talking about things that I haven't actually written on the board yet. Okay, so check this out. So if we have pi k of On, and say let's call this homomorphism Jnk to pi k plus n of Sn. So if we stabilize the orthogonal group coordinate, and we have an action of On plus 1 on Sn plus 1, when we do our J construction to that, which one do I want? N plus 1. Okay, I've written these in the wrong order. That's too bad. K plus N plus 1 of Sn plus 1. You can run through and check with this. This definition is not so hard to check, that this diagram commutes. So in fact, you can stabilize in the n coordinate, and in the limit, you get something called the J homomorphism that goes from the kth homotopy group of the orthogonal group to the kth stable homotopy group of spheres. This is something we know by Bott periodicity. So this is Z2, Z2, 0, Z, 0, 0, 0, Z.
You don't even sing the song.
You want to sing it? Z2, 0, Z, 0, 0, 0, Z. Yeah, it's the Bott periodicity song. So we know what these homotopy groups are, and these are a lot harder to figure out. But the J homomorphism is one of these really powerful tools relating, like, this is kind of geometry here, to stable homotopy theory. So somehow this entire picture that we're talking about is sort of straddling the line between these two, because now the J homomorphism becomes one of the most important parts of the actual computations of the things we're interested in. So J homomorphism, here's a theorem of Adams. So Adams wrote a series of 4 papers called On the Groups JX, where he computes the image of the J homomorphism in a very smart way, using some stuff I'd love to talk about on a different day. So if Jn is defined to equal to the image of the J homomorphism in 4n minus 1, or do I want 4n? Uh-oh. Have I lost the plot? Not sure any in the audience is really concerned. There might be a minus 1 here. So if we consider the actual order of the image of the J homomorphism, then yeah, I think I want 4n minus 1, because these are the degrees where you get a copy of Z. So this is 1, 2, sorry, 0, yeah, 1, 2, 3, 4, 5, 6, 7. So in the copies where we get an image, a copy of Z, we want to think really hard about how big is the image of this J homomorphism. Turns out Jn is equal to the denominator of the nth Bernoulli number over 4n. So the Bernoulli number came back. So where by denom I mean the following. So if Q equals A over B in reduced form, so the GCD of A and B is 1, then we define the numerator of Q to be the absolute value of A and the denominator of Q to be the absolute value of B. I throw in the absolute values because the Bernoulli numbers can be negative, and these are positive. So somehow, you know, this is an entire story. So Adams computes what is the image of the J homomorphism. Okay? So now going back to this Kervaire-Milnor picture. So knowing they already knew all this stuff about Adams, and they were able to do a bunch of arguments using obstruction theory to figure out what is this minimal possible Pn. Let me find my notes. Theorem. So this is the Kervaire-Milnor in the Bernoulli numbers paper. So again, so M, almost parallelizable. Then the topmost Pontryagin number of M is divisible by Jn times An, sorry about that, times 2n minus 1 factorial, where An is just like a bookkeeping variable. So this is 2 if n odd, 1 if n even. Moreover, there is a manifold M0 for n, just to note that it's special, which attains this bound, or attains this value, sure. So it is a sharp bound. In each of these dimensions, you know that this value divides your Pontryagin number, And you can actually find something where it is equal to that Pontryagin number. And I think I wanted to say closed here as well. To try to find this manifold, you go through the Pontryagin-Thom construction. You just have something like, okay, well, we have some homotopy class and some framed bordism group. So there's got to be some manifold that corresponds to that. It's sort of a non-constructive proof as far as I understand it. But it's possible I don't understand it at all. I'm just saying things to you now. Okay, so that being said, now we can tie everything together and we have our magical MM, which is the smallest possible signature for such manifolds. So corollary. So our signature of such a manifold, like we said, it's this Ln times Pn. And then we can start expanding. It gets better, don't worry. This is about as worse. This is about as bad as it gets. So it's not so bad. So we can simplify a little bit at this point. Say 2n minus 1, 2 to the 2n minus 1 minus 1. So now this 2n minus 1 factorial and this 2n factorial just leave a 2n. I've taken one of those 2's and I've canceled it out of this exponent. That's all I've done here. Bn times jn times an. And then is going to be divided by n still. But like we just said over there, somewhere over there, Adams decided that jn is the denominator of bn over 4n. So what I should have done is actually put an extra copy of 2 upstairs so that we can gather the bn and the jn together and get 2 to the 2n plus 1, 2 to the 2n minus 1 minus 1. And now we have the numerator of bn over 4n times this mysterious, not really mysterious, I spelled it out already, an. And this is as good as I'm going to leave it for now. This is what I'm going to call my mn, magic number. So every manifold that's closed and almost parallelizable and smooth in dimension 4n, its signature is divisible by this stuff. And moreover, there is one thing whose signature is that. Let's look at an example. Let's choose an n and then plug in numbers, okay? This is very dusty now. Okay, so example, n equals 2. All right, so 2 to the 2n plus 1 is equal to 32. 2 to the 2n minus 1 minus 1 is equal to 7. An is 1 because n is even. And the Bernoulli number, using the topologist ordering, is 1 over 30. So therefore, the numerator of bn over 4n is just 1. Nothing's going on there. Therefore, our magic number mn, which was equal to the signature of our m0 in degree 8, dimension 8, this is 2. This is now, right, this is just 32 times 7, which is equal to 224. And of course, this is 8 times 28. So we found our 28. Now we just have to figure out what to do with it, right? Promised you I would get a 28, and there it is. Okay. Moving along. Okay, is there anything that I forgot to mention about this part of the story that I should mention immediately? Oh, we're going to see. Yeah.
Am I also expected to find that the 8 has to do with the gamma?
Yeah. I pulled out that 8 because all of these manifolds, their signatures are divisible by 8. So I might as well just look at what is the other thing. How much other stuff is there?
Okay, so I should think of this 28 as the stuff I can surge away, right?
That's the stuff that's how much stuff you can't surge away, because the 8 is measuring that. Yeah. It's grouped with the 8. Yeah, the stuff that you can serger away is not captured by the signature. It's all signature 0 stuff. Okay. Good. I need a water break. Does anyone have more questions before I jump into the next little part? That was kind of like a fast assault of just random stuff.
So what's like the history of this? Like what year did someone write this down and say, wow, 8?
This is like, well, I mean, the 8, the WoW 8, that comes from like the classification of intersection forms. This is actually like an indefinite, even, non-degenerate intersection form. Its signature is divisible by 8. So this 8 is just always there in the algebraic side too. And so our manifolds that we're considering, their intersection forms just have those properties. So we can conclude already that their signatures are going to be divisible by 8.
This theorem's like from the 60s.
60s, early 60s. So some of this stuff was started in the late 50s already. The Adams papers about J homomorphisms, I believe, were early 60s, or they started in the early 60s. I should have been more careful about checking the dates on things. I can look at the date for the Kervaire and Milnor paper, like groups of homotopy spheres, because that's when everything sort of like accumulated and people were like, oh yeah, this is definitely true. Yeah, that was 1963, group of homotopy spheres 1. Yeah.
Was Adam's result also well known by the time that for learning Kervaire, or was this like
Yeah, like Adams, the series of papers J of X. I'm not actually sure like he was done those already by the time they published this, but they were all very close. They all talked all the time. So like everybody would have known. Like when someone proves like this is the image of the J homomorphism, everybody would have known about it because it was such a big deal at that time. So all of these little bits and pieces, the Hirzebruch Signature Theorem, everybody knew about it because it was just this monumental result.
And this intersection form stuff didn't come till later.
That was, I think, actually, I saw today that the first definition of the signature of a smooth manifold was by Hermann Weyl in like 1924.
Oh, wow,
So the intersection form, yes, really long time. I think it's probably even originating in like Poincaré's work.
yeah, that makes sense. Different forms and stuff.
Yeah, and like going to Poincaré duality to do this, so like Poincaré Lefschetz and stuff.
Which is like direct cohomology, Stokes theorem, and stuff. Like, I mean,
Yeah, and like I think, I'm not sure when they would have worked it out in the singular case, but like probably 20s and 30s as well. Like that's when Alexander, I think, was doing cohomology, singular cohomology. Yeah, I really wish I should just quit math and just be like a math historian, because the story of all of this topology stuff is so amazing.
mathematicians were so smart in like the 19th and 20th century. Like crazy.
Yeah.
Because crap.
Oh yeah. Well, I mean, it's sort of like the results that we still care about now, or like the biggest, most important ones.
Yeah.
I think it's easy to get that impression, but there were also like, yeah, there were way fewer of them, fewer opportunities, so you'd have to be like amazingly smart to get one. Sure. Okay, good questions. Okay, so now we're going to go to groups of homotopy spheres. Finally. Okay, so theta n is going to be the set of sigma which are homeomorphic to the standard sphere modulo h-cobordism. And like I probably should be saying homotopy equivalent, but for this talk I'll just say homeomorphic to emphasize the fact that the order of this group is measuring how many exotic spheres there are, the number of different diffeomorphism classes that you can stick on top of the standard sphere. And so the fact, it's not obvious by the definition, but this is a group. So sigma connect sum sigma prime is still a homotopy sphere. I'll just say H sphere, whatever. The inverse is, so negative sigma is actually just sigma with the opposite orientation. To see this is kind of cute. So why is that? Well, first of all, we know that sigma disjoint union sigma bar, this is the oriented boundary of the cylinder, right? Right, so it's looking like this. Here's our sigma, sigma bar. So what we can do is form like an internal boundary sum on the same manifold. It's a really crappy, good thing Tom didn't see that. So yeah, we can do this internal connected sum. So now the new boundary is sigma connected sum sigma bar, and our manifold just has this little hole in the middle. Because we've just done this really simple surgery to the cylinder, you can take like the core circle, kind of the thing that goes from here to here, put a little trivial normal bundle around that very easily. And if you take that out and do the complementary surgery by gluing in two disks, you get something that looks like this. I can do some colors. So we want to take out this little disk and glue in the complementary disks like this. Here's one of them, and the other one's in the back. So then you compute that this thing is contractible. So like we saw in the first talk, the very first thing I mentioned was that if you have a smooth manifold, a simply connected smooth manifold that bounds a contractible manifold, by the h-cobordism theorem, it's a standard sphere. So this means that after doing these surgeries and getting a contractible manifold, the boundary has to be standard. So that the connected sum of sigma and sigma bar is really diffeomorphic to the standard sphere. So that's why it's an inverse in this group.
How do you think about that in terms of like, if I just take two copies of S2, right, and I have S2 and then I have its like opposite one, and then what do I do with this? You know, how do you?
What do you mean?
Like if I do this copy, right, but instead of sigma and sigma bar, I take like S2 and S2 bar, right, and then so I have one sphere, and then I have like the flipped version of it. What is that like, just in terms of the spheres, the copy?
I mean, like in terms of this, you'd know it would have to be like the trivial sphere, right? So S, you're saying like S2 connected sum,
Yeah.
S2 bar.
Yeah.
How does this work? If you reverse an orientation,
Because then you're just taking like.
I think it's still diffeomorphic, isn't it? Isn't there an orientation reversing diffeomorphism of the even dimensional spheres? Or is it the odd ones?
Oh yeah. Oh yeah, we did that in Spiro's class. I think it's the.
Well, like because it's a group, right? Because it's a group, identities are unique.
Yeah.
So it would have to be at least h-cobordant to its opposite orientation. So it would be,
So this
if
is
the
not-
dimension were more than 5, I could say it's diffeomorphic. But yeah, it is diffeomorphic.
It is.
Yeah.
So this is like not interesting.
Kind of interesting to see that it is diffeomorphic. But yeah, you don't construct an interesting manifold by doing this. You just get S2 back.
You just did it, so.
Yeah. S2 with some orientation. Yeah, I forget how that works. I'm pretty sure you can just get an orientation reversing
Yeah, I
diffeomorphism.
remember it depends on like the odd or even parts of the.
Yeah. Okay, so it is a group. Inverses are just taking the opposite orientation. That's cool. Well, I forgot to mention with the intersection form, if you take the opposite orientation, you end up getting the opposite signature because you just flip the fundamental class. Okay, so there's a special subgroup which is relevant to us and all of this stuff that we just talked about, called BPn+1. This is the set of homotopy spheres in dimension n, so that sigma is the boundary of a W which is parallelizable. So the BP stands for bounds parallelizable. Okay, so all of the homotopy spheres that we've thought of so far are in this special subgroup by construction. We did all this plumbing stuff. By the surgery procedure, we kind of assumed that it had to bound a parallelizable manifold in order to get our trivial or normal bundles. So all of the homotopy spheres that we've already considered so far live in this thing. So here's something that we can figure out now based on what we've done. So if sigma is something bounding a parallelizable manifold in dimension 4n, so we have some 4n dimensional manifold whose boundary is a homotopy sphere. Say sigma is the boundary of W. And if the magic number doesn't divide the signature of W, then sigma can't be standard. Why? Because if it were standard, we could glue on a disk to form a closed manifold whose signature is invalid. So the signature of a co-boundary is actually can be used as a check to see if your homotopy sphere could potentially be standard or not.
If my sigma is in BP4n, that means my n, like if I look at the n above, then it's, yeah.
Yeah.
Sorry, wait.
So sigma.
Yeah,
So
it's 4 minus 1. Okay, yeah.
Yeah, so the bounding parallelizable, this dimension refers to the dimension of the co-boundary, W. So if our W is 4n, then we're talking about theta's 4n minus 1. Yeah. I think there's about like 18 things that I forgot to mention by this point. So we'll just have to come out a little awkwardly as we go. But we're almost done. Okay, so for example, like I said, the boundary of the E8 manifold is not standard. I think I mentioned that already. I also think I forgot to explicitly say the most important thing, which was if our manifold, a 4n almost parallelizable manifold has signature 0, then you have no gamma 8s, and you can do surgery on it to turn it into something that's either contractible or a homotopy sphere of that dimension. I should just write that explicitly. So forgot to mention. Forgot to mention. So if, say, W almost parallelizable, oriented, smooth, all of that stuff, and sigma W is 0, then we can do surgery. If it's almost parallelizable and the boundary of W is either homotopy sphere or empty, like I said, then we can do surgery to make a W bar such that, depending on these two cases, W bar contractible, and i.e. the sigma was actually a standard sphere. Or in the other case where the boundary is empty, we get W bar is a homotopy sphere. So this was the most important part about studying the signature of our manifolds from the surgery perspective, is that the surgery tells us, or the signature tells us, whether we can continue to perform surgeries or not. So like you were saying, like the 8 times 28, like that 8 times 28 is all of the stuff we can't do surgery to. So if the surgery is just 0, our intersection form just looks like a bunch of U's. And so we can just clear out all of those U's and get down to something with no homotopy, no homology in the middle dimension. And so we're going to use this principle in order to form a bunch of arguments to actually compute this BPN. So now we actually get to, yes, this is the good page. This is the page I wrote today, so it's got to be the best page that I've got. Okay, so let's compute. Computing BP for n as a subgroup of theta for n minus 1. Okay, so notice the following. So if sigma is in this group, and suppose it's the boundary of 2 different manifolds. So sigma is the boundary of W1, and it's also the boundary of W2. And now let's let sigma 1 be the signature of W1. Sigma 2 is the signature of W2. So then, if we take W1 boundary sum W2 opposite orientation, this has boundary the connected sum of sigma with sigma bar, and this is diffeomorphic to the standard sphere. S4n minus 1. Sorry. And signature, sigma 1 minus sigma 2. Because the boundary is standard, we can close it up, cap it off with a disk, making say a W. What did I write in my notes? I just said W. So W closed, almost parallelizable, same signature. And so therefore, now we actually have a positive result using this magic number. So we know that our magic number must divide the difference in these two signatures. Right? This means if we take an arbitrary homotopy sphere in our BP group, choose a parallelizable coboundary, and take its signature, this is well defined modulo magic number. I don't want to quite do that. I want to hit 1. So what I'm going to do is take the number ON, where ON is just the magic number divided by 8. I know everything has this redundant copy of 8 in there, so let's just divide it out. And so what we can do is take our homotopy sphere, and then we take the signature of a coboundary divided by 8. So by this argument, this is a well-defined function. So this is a group homomorphism. So this is evident just by the boundary connected sum. Yeah, so blep. So this thing, connect sum, this thing is the boundary of this thing, boundary sum this thing, right? So psi of this is just, you just take this manifold, take its signature divided by 8, but we already know that the signature is additive here. And so this is exactly the sum of the psi's. Yeah. So it is a group homomorphism. That's a good start. C is surjective. Why? Can someone who's been paying attention tell me why this thing is surjective? Oh, fuck. Oh, no, I shouldn't have sworn. I'm sorry. Please edit that out, if possible. So we just have to hit 1. We have to find some manifold whose boundary is a homotopy sphere, so that when you divide by 8, you get 1.
The M0, right?
M0? M0 is too big. M0, the signature is the magic number, right? That's so if you plug in M0, you actually get 0.
Right.
But that's sort of the right
Your
direction.
E8, like that was.
Is it really the E8?
Sure, yeah. So if sigma is the boundary of E8, E8 was this thing that we manufactured to have signature 8. So this means that psi of sigma is 8 over 8. So we hit 1. That's cool. Why is it injective?
Because now this is M0. Well, I guess, right? M0 at least gets sent to 0, I guess.
M0 goes to 0. Yeah.
You want to show that M0 is the only thing that gets into 0.
Up to whatever relations. Yeah. So yeah, we'll see. Okay. I should underline these, make it a bit more easy to read. Oh yeah, it's so exciting. Okay, so suppose we have one of these things that spits out 0, meaning, so there exists a W parallelizable so that the boundary of W is equal to sigma, and our magic number divides the signature of W. So that's what it means to be in the kernel. So let's say sigma of W, let's pick one, is k times mn for some k in the integers. And then we appeal to our m0. We take W prime. So start with W, and now take a connected sum. So W has a boundary, but let's connect something into the interior. So here's our W. And let's connect some k many copies of our magic manifold with the opposite orientation. So that signature, right? So what we're doing is we have this weird thing with many signatures, and we're just gluing it in to cancel out whatever signature already existed in W. So this means that the signature of W prime is just exactly equal to 0. So since we haven't modified the boundary, so the boundary of W prime is still the same homotopy sphere, but now W prime has signature 0. So we can surger it to get a contractible manifold, meaning that our boundary is homeomorphic to the sphere 4n minus 1. Diffeomorphic to the sphere 4n minus 1. So we get to, use this thing to kind of take care of whatever indeterminacy there is in these signatures. We can just like do the division algorithm so that whatever our co-boundary is, the signature goes from 0 to on minus 1. And so this gives us our isomorphism between the bound parallelizable and this group. So that's what we just computed. We just figured out that these bound parallelizable in these dimensions, that's divisible by 4. Remember, we've only done these dimensions so far. We actually figured out what this group is. So psi from B, P, 4n to Z mod ON Z is an isomorphism. And I don't think I'm going to write out what ON is in excruciating detail this time. Oh, I guess I did in my notes. It's okay. Just to remind everybody. So we're defining by 8. If you go and look up what mn was and divide it by 8, you're going to get this. So you're just reducing the exponent on the 2. We have our an numerator bn over 4n. And so example, if we take BP8, so contained in the group of homotopy spheres of dimension 7, this is isomorphic to Z mod 28Z. So this is why our 28 is important. That's how many of those homotopy spheres there are. So in the very, very little amount of time that's left, I have to say, well, what else is there? We've only chosen a very specific subgroup. So what other homotopy spheres exist? I have 15 minutes because we started late. Oh, okay. Well, I don't want to like take up everyone's night, but I'm pretty close to done. I'm just kind of saying like, this is what I wanted to get to. This is what I wanted to get to. Now it's like, okay, well, what have I left out? What is all of this stuff that I left out that we haven't actually discussed at all, and we're not going to because I want to stop talking about this. What about the rest? Okay, so here's some black magic. There exists a short exact sequence. This is actually not really hard to establish, but you have to have the right interpretation of the J homomorphism. So we have the subgroup BBPN plus 1 living inside theta n. The quotient by this is the co-kernel of the J homomorphism. So all of that stuff involves the image of the J homomorphism. Now you get all of the rest of the stuff from the stable group of homotopy spheres. So this is stable homotopy theory. Like modulo the geometric stuff that came from the orthogonal group, this is just stable homotopy theory. Somehow exotic spheres are governed by stable homotopy theory. I'm not going to argue against that. And moreover, this is something that we don't really need, but it's very good to know. A mathematician named Broomfield, I think this was in the 70s, showed that this splits. So theta n is actually isomorphic to the direct sum. You have things that bound parallelizable manifolds, which have been covered by all of this stuff that I talked about for the last 3 lectures. And then you have things in the co-kernel of the J homomorphism, which are framed h-cobordism classes of spheres, modulo some stuff. Yeah, ingredients of the proof, J homomorphism, framed surgery is another big thing. So I've only talked about unframed surgeries, but framed surgeries are very important as well. These are the relations between manifolds and framed h-cobordism groups. So in dimension 7, this is something that one can go compute or look up for themselves. The order of the 7th stable homotopy group is 240. And so atoms, so the image of the J homomorphism in degree 7 is equal to, what was that? The denominator, denom, of B2 over 8, n is now 2. And this was equal to the denominator. If you just plug it in, you get negative 1 over 240. And so you get 240. So the J homomorphism is surjective in this degree. And so the entire group of homotopy spheres in degree 7 is Z mod 28. And in order to figure that out, you need to know stable homotopy theory. But this part is like the fun part for people who don't know stable homotopy theory yet. And you can build up this entire really interesting theory about manifolds and signatures and things like that. So it's a good topic for a seminar talk. And then in the final remaining minutes, I have to mention what happens in the other dimensions. Oh, that was the wrong one. Okay, that's too bad. I'll just leave this over here. So plus im j, yeah, J7 surjective. By that, short exact sequence means that the entire thing is Z mod 28. So, and what about other? So we've only discussed n congruent to 3 mod 4.
I have a question. Brumfield, isn't it?
Brumfield, yeah.
Brumfield. He showed that short exact sequence splits every time for all the n.
All n, yeah, every dimension.
Okay, so that implies that at least your group of homotopy series is a finite group, right?
Because it's an extension of a finite cyclic group, and these are always finite by Serre, who showed that the groups of homotopy spheres, stable homotopy groups of spheres, are finite. So these are always going to be finite, and this is finite.
Should I have? Is there always to expect from the beginning that theta sub n should have been finite? Because like it's a huge set that's defined. So I don't know. Was there a shortcut to know that? Oh, I'm expecting a finite number, or like was this like shocking? Like, hey, this is kind of crazy.
I forget. Someone that I knew in grad school said some weird thing to me of the form like. No, I forget. I didn't believe it at a time, so I would say no, there isn't like an easy way to tell right away that there's only going to be finitely many. But there might be like a really clever way of doing it that you have to know a lot about to understand why it works. But I don't know it. Yeah, good question. Yeah, this is, yeah, extremely important to point out that, yeah, these are finite. That is a really surprising outcome of this whole story. There are only finitely many exotic spheres, as long as n is at least 5. In dimension 4, we don't know. We have no idea. So what about other dimensions? This one, so n even. This is pretty interesting. There is no surgery obstruction. You do a whole bunch of work, a lot of difficult work, to find out there is no surgery obstruction. So all of these are 0, and the theta n is just the co-kernel of the J homomorphism in these degrees. And if n is congruent to 1 mod 4, I mentioned that a similar story plays out, but instead of the signature, the relevant invariant is the Kervaire invariant. And so this is derived from something called an ARF invariant of a particular form. So that's a whole story. It's a little bit more complicated than the signature is, but not so much more complicated. So then once you move away from spheres, all of this stuff, Kervaire-Milnor, it turns out this is just step 1 of surgery theory. This is the easy case. This is the easy, no-brainer, baby kindergarten case. So where you go after this, step 2 is the surgery exact sequence. So the names that get put on this, Browder and Novikov. So in the 1960s, early 1960s, same time as Kervaire and Milnor, they were studying problems about if you're given like a simply connected homotopy type for smooth manifolds, like is there only one smooth manifold that realizes that? So I think they answered that affirmatively. Sullivan took their work and was able to put it into the form of not a spectral sequence, just a long exact sequence in a very clever way. And then later on, Wall, who is one of these gods of surgery theory, he did the non-simply connected case. So this is something we didn't talk about at all, non-simply connected surgery theory. So when you start putting fundamental groups into the picture, you start getting these complicated L groups. So the surgery exact sequence seeks to compute something called SX, the structure set. So in the differential category, let's say for n. So if we have a fixed n, this is going to be like the set of all closed n-dimensional manifolds with homotopy equivalences to x. And modulo some equivalence relation, I think it's concordance. So from here, you get these weird things called normal invariants, which are, I forget. I'm just putting this in. And then you get a weird surgery obstruction map. So normal invariants give you a surgery obstruction, similar to the signature. And these land in an algebraic mechanism called the L groups of pi 1x. So people who do surgery these days, one huge subset of those people are just computing algebraically these bizarre L groups for like random groups that you would plug in. So a lot of the modern day surgery theory that people do is very, very algebraic. Like a lot of the geometric developments have been done. I encourage you, go study surgery theory, absolutely study it, because there's so many cool geometric things going on. But you also, you'll probably hit a point where you're like, this is a lot of algebra that I don't want to think about anymore. And then ... So there's this exact sequence that you can use to try to figure out what are the set of smooth structures on a given topological manifold in terms of this weird, these weird structures that I'm not defining for you, in the hopes that you'll just be interested and go try to learn yourself. These L groups are kind of like a Bordism group for quadratic forms. Kind of cool. Okay, I have nothing else left that I want to say. So thank you very much for coming. That is the end of my talk. Excellent. Thank you.
So what actually happens when n is equal to 1? What breaks down in all this?
When n is equal to 1, like in dimension 4.
Yeah. Why can't we find all of them? Like I know that's like a big thing, but why in this picture can we see easily like, oh, if you plug in n equal to 1, then this fails or something?
So one thing was the h-cobordism theorem itself. So the main technique in that, which required a dimensional restriction, is something called the Whitney trick. I don't know if you've heard of that before. The idea is like you have this a handle attached onto a handle that was already there. And like the algebraic intersection between the attaching sphere and the belt sphere is 0. So you want to be able to actually physically slide this handle off. And in order to geometrically cancel those points, so the reason you want to assume simple connectivity is sort of you have these 2 points, you choose a path through one of your manifolds and choose a path through the other manifold. Simple connectivity says you can fill that in continuously with a disk. Now, Whitney embedding theorem says if the ambient dimension is large enough, you can change that into an embedded disk. And so this is why you need at least 5. So that embedded disk you can use as sort of like a framing to push one of the things off of the other thing and make a trivial intersection. So that's one of the main reasons, is just that the Whitney trick doesn't work. So h-cobordism theorem doesn't work.
So if you wanted a description when n equals 1, you essentially can't use any of this.
Yeah, there's like some stuff that you can still do. Like the whole story about intersection forms and all that still holds and stuff. It's just being able to conclude, like, so for example, you can have a smooth manifold. I think this is true in dimension 4. You can have a simply connected smooth manifold bounding something contractible, and yet it's, well, actually, no, I don't know that we know that, because we don't know that there are any exotic force spheres. But I'm not sure if that theorem is provable in dimension 4. But we use that like all of the time here.
So I actually don't know much about exotic spheres, but isn't there like a big thing about classifying exotic spheres or something like that? Like, is that a big problem or something?
I guess so. I mean, this is what this whole picture is
Because I guess
talking about.
I was just gonna say, like, we have an exact classification of them all for all n, right? They're just the sum of these 2 groups.
Yeah. So it just comes down to like, for these, you just have to compute some Bernoulli number stuff. And then for these, you have to do stable homotopy theory. And you know that it's just like a trivial extension.
Are all of them going to be smooth for all n?
Like, are the homotopy spheres smooth? Yeah. This is specifically like we chose smooth manifolds.
Okay.
Yeah.
Do you know which of them are going to be complex? I know n has to be, obviously even or something, but like, is there a classification of which ones can be complex?
And that's something that only depends on the homotopy type. Like, I'm not sure. Like, I feel like it doesn't depend on which smooth structure you pick. But I don't know. Am I wrong about that? Do you know?
Well, you could have.
S6 maybe. I don't know. We'll see.
Because you could have 2, like, I might be speaking out of my ass. Are you recording, by the way? Okay. I might be lying here, but like, isn't it like if you take P2, if you take the smooth structure of P2, and then you can have its opposite orientation defining a different smooth structure, but they're the same as complex manifolds.
Huh?
I think that might be true, but I could be.
So you're saying like CP2 versus CP2 bar?
Yeah, I might be lying that I think they have underlying different smooth structures. Or is it the other way around? They have the same smooth structure but different complex structure. That's
Yeah. Yeah, this is literally just the same smooth manifold, but the
different.
opposite orientation. Yeah, exactly. Because like the orientation is already induced by the smooth structure, so it couldn't be the same. Yeah, I misspoke. Yeah, the orientation is induced by a complex structure automatically. Yeah.
Also,
Yeah.
which spheres are
complex?
Like, I think if a sphere were to be complex, it'd have a complex, like, complex with manifolds. So it would have to also be like a projective variety. And particularly it has to be Kähler, so the only one you'd allow is S2 now. Do they have to be projective?
Did you just prove a huge open problem?
Okay, sorry. Like, I was thinking Gaga, I don't know if I'm missing an assumption.
Maybe like.
It's not sure that every smooth sphere or every.
Well, if you somehow can conclude that the sphere of this complex has to be Kähler, then you have a problem because only the 2 spheres Kähler.
What does Kähler condition mean again?
Say you have like a symplectic structure that's compatible with the complex structure.
I don't know. Is there a characteristic class formulation of that? It's like the only way I can think about these things.
I don't know. Someone was interested in these kind of things. But
Yeah.
Okay.
Like,
it's definitely a vanishing of some Steffel-Whitney or something like that. I can't remember.
And it's not just W2. Like, it's not just W2 vanishes. Or has an integral lift. That's just a spin C structure. Yeah, I'm not sure. But I know that like S6, I'm pretty sure it's S6 is still like a wide open problem.
That one's almost complex, but unclear if it's complex or not.
Yeah. I forget how this works. You can rule a lot of them out based on like Pontryagin numbers.
Yeah, I can't remember what the thing is.
I did work out that argument
If
once.
even ones are non-zero or even ones are something like that.
Yeah, it's because you know if it's complex, you get Chern classes, so you can relate that to the top
exactly.
Pontryagin class. I just don't. Yeah, I figured it out one time. You have to use like the Chern character. Somehow using the Chern character gives you the answer.
So is there other stuff you can do? Like you have your theta, and here's like I just mod out by the diffeomorphism type of my stuff. So like how much of this machinery? I guess now I'm curious about this discussion. How much of this machinery can like I do if I just instead of modding out by diffeomorphism type, I mod out by some other type?
So like, I don't know. Maybe you want like homotopy equivalent. Well,
Like I assume like you're keeping more information, so I would hope things would be nicer. But
that kind of gets subsumed in the surgery exact sequence. It's sort of like where you suppose that like X comes from some category and you want to think about all homotopy equivalences of things that are living in another category, like with more